Good afternoon, everyone. Today, we are very happy to have Dalimil Mazáč from IIS to tell us about his work on bootstrapping boundaries and the Branes. Please take it away, Dalimil.
Okay, very good. Thank you so much for the introduction, Dongsheng, and thank you for inviting me to give this talk. It will be based on a paper that came out in December, done in collaboration with some fantastic authors, Scott Collier and Yifan Wang. Scott is a postdoc in Princeton, and Yifan is now a fresh faculty at NYU. Okay, so to a large extent, the talk today will be about conformal field theories. And the first thing you should know about conformal field theories is that they're absolutely great for several reasons. One of the reasons is that CFTs are cornerstones in the space of quantum field theories. So this means that for the large class of quantum field theories can be thought of as an RG flow between some UV CFT and an IR CFT. So if we ever want to have a chance to understand the space of quantum field theories, we should probably start by understanding the space of conformal field theories as well as we can. Secondly, CFTs also provide a precise definition of quantum gravity, at least in an anti-de Sitter space. So this is, of course, just a statement of ADS CFT. And finally, in the context of 2D CFTs, which is what we'll focus on today, 2D CFTs provide the worksheet description of string theory. Whoops. So if you want to understand this, the landscape, the classical solutions of string theory, you should try to understand 2D CFTs. Finally, not only that they are very physically relevant, but they can be also formulated very precisely mathematically. So there is a very precise and highly effective axiomatic formulation of conformal field theories, which usually goes under the name of conformal bootstrap. Of course, there are some axiomatic formulations of fairly general classes of quantum field theories, but they are not as effective as in the case of CFTs. So in the case of CFTs, we can really use these axioms to make very precise quantitative predictions, as we will see today. So what is it? Now let's focus to 2D CFTs from this point on. So what is a CFT? Well, in a way, we can think of a CFT as a machine which is computing correlation functions. And well, eventually we are going to consider boundaries, but let's not consider boundaries yet. So what is the most general correlation function? The most general correlation function consists of picking some Riemann surface, so some two-dimensional closed manifold with some complex structure, and decorate it with some punctures where local operators live. Okay, and a CFT is just a machine for assigning a number to such an object in a mathematically consistent way. Now, what are these local operators? Well, for a given CFT, they can be thought of as well, they're labeled by irreducible modules in the Hilbert space on a circle. So the only closed one manifold is S1. So this should be S1. And we can consider the Hilbert space of the CFT on a circle and decompose it into irreducible modules of the two copies of the Virasoro algebra, the left moving and the right moving Virasoro algebra, some central charge C. And well, these are labeled by the central charge and a pair of scaling dimensions or conformal weights H and H bar. And there is a one correspondence between these i's and primary operators that we can insert in this Riemann surface. Okay, so part of the data specifying the CFT is this collection of central charge, H and H bar. And this is almost complete. The only other thing that you need to specify a CFT is to give the three-point couplings between any triplet of primary operators. So these are called CIJK. Now, once we have this data, all correlation functions on closed Riemann surfaces are determined by this data. So by the central charge, the conformal weights, and the structure constant CIJK. Well, why is that? The reason is that we can cut any Riemann surface into three punctured spheres by cutting along S1s. Okay, so here is an example of a genus 2 surface that we can cut along three closed loops, I, J, and K, and we insert a complete set of states here, and there, and this gives us an answer for the correlation function or the partition function on this surface. Well, this is not a full story, because usually there are many inequivalent sawings of a given Riemann surface using these closed curves into three-punctured spheres, and the equality of all of these sawings gives us constraints on the original data, on the set of on the set of weights and the three-point couplings. So you could say that the conformal field theory is a collection of these numbers, the conformal data, which is compatible, which is in such a way that all correlation functions are independent of how we saw them together. And it turns out, as was proven in the 80s, that in the absence of boundaries, the set of necessary and sufficient constraints which guarantee that all correlation functions are consistent just come from considering a sphere with 4 insertions and the torus with 1 insertion. Okay, and the sort of big goal in this field will be to try to classify all 2D CFTs, in the sense to classify the set of such data which satisfy these constraints. But so far, there's been relatively little progress on this goal. Well, there's been some progress in the context of so-called rational CFTs, which is a fairly large but still kind of limited class of CFTs, where we only have finitely many irreducible representations of the full Cairo algebra. But in all other CFTs, so in the irrational CFTs, where we don't have this finiteness condition, there's been very little progress in understanding. In fact, there are very few examples, explicit examples of irrational 2D CFTs. So in some sense, you know, it is often said that we understand 2D CFTs better than higher D CFTs, but from this point of view, it's not really true, because the generic 2D CFT is irrational, and we understand as little about irrational 2D CFTs as we do about higher D CFTs. So, yeah. Okay, are there any questions so far? I should ask you, but please feel free to interrupt me at any point if you have a question. All right, so this is the story in the absence of boundaries. But the rest of the talk today will be in the presence of boundaries. So what are they? What are the conformal boundary conditions for CFTs? This is a subject that goes back specifically to John Cardy's seminal work. The conformal boundary condition is just the situation where we consider a CFT on some half plane, and then we have a boundary of the half plane, which is here on the real axis. So the CFT only lives in this upper half plane, and the different boundary conditions are labeled by some index alpha. Now we'll assume that this boundary condition is conformally invariant, which is to say that the holomorphic and anti-holomorphic stress tensor agree with each other on the boundary condition. Another way to say this is that there is no energy leaking out of this half space, so that there is no energy flux across the boundary. Now, once we consider CFT, it's very natural to consider also boundaries, because it's natural to give boundaries to Riemann surfaces essentially. But not only that, they also occur very naturally in various places in physics. For example, in the context of condensed matter, they describe boundary criticality. I should also say that all of this has an analog in higher D. So boundary conditions, conformal boundary condition also exists in the context of higher D CFTs, and they have also been studied by many people. So they are natural in condensed matter. In the context of string theory, they describe the interaction of open strings with D-branes. So if you want to have a string theory which has open strings, then you'll need to consider boundaries, which is where the worksheet of the string ends, and the different boundary conditions correspond to the choices of different D-branes. And finally, in the context of ADS-CFT, boundary conditions describe the so-called end of the world branes, and I'll say a little bit about those at the end of the talk, although it will definitely not be the main focus. Okay, so now what is the analog of the previous statement of the general correlator? Well, the general correlator in appearance of boundaries looks something like this. You know, it's a Riemann surface which is not closed. It can have these boundaries. So here is a boundary, here is a boundary, but this is supposed to be a hole. So there's no boundary living here. And the most general correlator consists of placing a bunch of local operators in the bulk. So these would be like the closed string vertex operators, and choosing various boundaries and putting some boundary local operators on those boundaries. In particular, we can also have boundary operators which change different boundary conditions into each other that sit at boundaries between different boundary conditions, such as here between condition alpha and beta. Okay, so the space of local operators living on boundary conditions on boundaries is in general independent of the set of local operators living in the bulk. So what is the space of local operators living on the boundary? Well, using radial quantization, it can be described as the Hilbert space on an interval. So here's a picture of an interval with time flowing up, so the strip, if you wish, and we choose a boundary condition alpha on one side and a beta on the other side. And if we quantize the theory on this geometry, then we are going to get a Hilbert space, which is a representation of one copy of the Virasoro algebra. That's the diagonal copy, which acts diagonal on left and right movers. And we can decompose this Hilbert space into irreducible modules of this Virasoro symmetry. And what we'll find is a collection of these irreducible modules, which are labeled by central charge and the weight. So in this case, there's only one conformal weight, not two, because we have only one Virasoro. And these irreducible modules correspond to the primary operators. So the primary operators are labeled by the boundary conditions alpha and beta, which they change, and some index I. Now, what do we need to specify to give the most general boundary condition? Sorry, to give the most general correlation function of a CFT with boundaries? Well, it turns out there is only two kinds of additional CFT data that we need to specify. One of them is the so-called boundary 3-point functions. So these look like a disk with, in general, 3 independent boundary conditions chosen on the boundary and local operators inserting in between them. So this is some discrete set of data that we can call C twiddle IJK alpha beta gamma. And besides that, there is another set of data, which is the so-called bulk to boundary OP coefficients that are essentially the disk amplitude with some bulk operator inserted inside, and a single boundary condition on the boundary and a local operator on the boundary. So these are labeled by a closed string state, an open string state, and a choice of boundary condition. And we will call them B alpha ij. And now any correlator with boundaries, such as this one, can be decomposed by cutting either along S1s or along intervals to be expressed as a linear combination of this data. So any correlation function can now be expressed using the central charge, the weights and 3-point couplings in the closed string sector, and the weights, 3-point couplings in the open string sector, and also this bulk to boundary that you can think of as a closed string to open string amplitude. And again, we need to demand that all correlation functions are independent of the choice of Soink. And as was discussed by Lavallin, the necessary and sufficient conditions on this CFT data for any correlator to be independent of the choice of a Soink consist again of the 4-point sphere amplitude, the 1-point torus amplitude, and 4 additional constraints involving the boundary operators. So okay, this is just the usual conformal bootstrap on the boundary. This is like a boundary 2-point function with one operator insertion, and this is the so-called bulk to boundary crossing. And finally, what we'll focus on today is this one, which is the consistency of the cylinder amplitude. In fact, we'll focus on a very special case of the consistency of the cylinder amplitude, which is the so-called Carde condition. The Carde condition in the case when these two boundaries are the same. Okay, so the rest of the talk today will be devoted to exploiting the consequences on the CFT data of the consistency of the cylinder, where we choose we choose the identical boundary condition on both ends of the cylinder, some boundary condition alpha. And now there are two inequivalent ways of cutting this. One is along the S1. So this is the closed string channel, where we have S1 states propagating in this direction, or we can cut it along the interval. And now we have open string states propagating in the other direction. Okay, maybe are there any questions so far?
Hi, Dalimil, maybe I can ask one.
Yeah.
Just to break the ice. Hi. The second one of the constraints in the boundary case looks a bit funny in respect to the others because there's no crossing there. So
this one?
Yeah. You have only one expansion.
I guess it's only interesting when these two conditions are different, because then you can fuse this operator either to the left or to the right, and that gives you an equivalent. Yeah.
Okay, so if the difference is non-trivial, otherwise it's trivial. Yeah.
I think. That's right. This is only interesting if you want to understand boundary changing operators.
Well, I guess there is still one constraint, which is that there are some smoothness that maybe in the finite case, if you are in a rational case, you could use, right? There's some point in which the three operators are aligned, and that should not diverge, but the conformal box will. But I don't know if that's what the one did. Okay, thanks.
Maybe, thanks. Yeah, thanks. It's a. All right. So today, as I said, we'll only use this condition, and we'll use it to learn some new bounds on on boundary entropy. What is the boundary entropy? It's this number, which I'll call G of alpha. So we'll choose a boundary condition alpha, and the boundary entropy is just the disk partition function. So we have the CFT living in the disk, boundary condition alpha on the boundary, and this amplitude gives the boundary entropy. And by the way, it's also the same as one of these bulk to boundary OP coefficients. Well, which one is it? It's the one where we put identity both in the disk and on the boundary. So it's a special case. It's a special case of this object where both psi and phi are the identity operator. All right. So the main goal of the talk today is to derive some upper and lower bounds on this number, starting from the Carty condition. But before I do that, let me talk a little bit about the physical significance of this number. So one thing you can say is that the boundary entropy measures the number of degrees of freedom of the boundary condition, and in particular, it decreases under boundary RG flows. So if we pick some fixed bulk theory, bulk CFT, and there is some RG flow on the boundary, which changes the boundary condition from some UV to the IR, then the UV boundary entropy is greater than the IR boundary entropy. And I'll say a little bit more about why G measures the number of degrees of freedom once we discuss the cylinder amplitude in more detail. And another type of physical significance of this boundary entropy is that it measures the d-brane tension in the context of string theory. So for some brane, d-brane, specified by some boundary condition alpha, the tension is proportional to this disk amplitude, to the G, because it essentially measures the coupling between open strings and the d-brane. And there's also some factor of 1 over G string, and you need to add factors of string length to make it dimensionally correct, but this is the basic idea, that tension is proportional to the boundary entropy. Okay, so now let me discuss the Carty condition, so the consistency of the cylinder amplitude in more detail. Well, the first preliminary statement is that a boundary condition corresponds naturally to a state on the circle. This is just the boundary state. The way it works is that you can make a conformal mapping to the cylinder, and then if you put this boundary condition alpha on an end of the cylinder, you can just think of it as creating a state on S1. I mean, that's just a sort of a trivial consequence of this picture. And the gluing condition that we originally wrote in the half plane, that the holomorphic and anti-holomorphic stress tensor must agree on the real axis, just becomes a statement that for all for all integers, the Virasoro modes, the left and right moving Virasoro modes must act in this way. So there's a sort of identity between ln and l minus n bar acting on the state. So this is a constraint on the possible boundary states. It's not a complete set of constraints, but it's one of the constraints that are important. And there is it is possible to find a complete set of solutions of this condition in the Hilbert space on the circle. And these are the so-called Ishibashi states. So Ishibashi states are in one-to-one correspondence with scalar conformal primaries of Virasoro times Virasoro bar. So let's pick some scalar primary whose scalar just means that the h and h bar are equal to each other. And then let's consider this linear combination of states which is just a sum over all the descendants, well, all the combinations of L's, and we act with the same set of L's on the left moving half and the corresponding and the same set of L bars on the right moving half. And if these states are normalized, it's possible to check that this state satisfies this constraint. And in fact, is the most general solution of this constraint is a linear combination of such Ishibashi states. Now, an Ishibashi state is not necessarily a boundary condition because it doesn't satisfy the Carde constraint. But what we have learned is that a general boundary state can be expressed as a linear combination of these Ishibashi states. And in fact, the coefficients in this linear combination are precisely the bulk to boundary OP coefficients of some bulk primary phi into identity on the boundary. So this is what we used to call B alpha I identity. Identity is the identity on the boundary, and I is the I in the bulk. And you see that in particular identity Ishibashi state generally will appear in this combination, and we'll single it out. So this is the first term corresponding to the identity in the bulk that whose coefficient is precisely the boundary entropy. This is just the definition of boundary entropy that I gave earlier. And then there is a sum over the remaining bulk primaries. Okay, so now with this information, let us express the cylinder or annulus partition function in terms of either the closed string or the open string primaries. Okay, so here's a picture of the cylinder partition function. We'll set it up in such a way that the length of the circle is 2 pi, and the length of the cylinder is pi t. So t is some positive real number. And by conformal transformation, this is equivalent to the annulus defined by concentric circles with radii 1 and e to the minus pi t, where the boundary conditions are at the edges of the annulus. Now, if we cut along the closed string channel, so along the S1, we get the following expression for the cylinder partition function. It's just the overlap of two boundary states evolved by the closed string Hamiltonian by amount pi t. And now if we plug in for each of these boundary states this sum over Ishibashi state, we'll find the following expression. Well, it just contains these bulk to boundary OP coefficients squared times this overlap of an Ishibashi state evolved by bulk Hamiltonian. And the point is that because the Ishibashi state is completely fixed by conformal symmetry, this is some object fixed by conformal symmetry alone. In fact, it is equal to a character, as we will soon see. Okay, it's right here. Okay, so this expansion of the partition function just becomes this expansion. The first term comes from the identity, and it contains the boundary entropy, which we can assume to be positive and real. So G is positive and real. And there is a boundary character of the vacuum. And then there is a sum over the non-vacuum primaries in the bulk that looks as follows. And it's a sum over scalar primaries because only scalar primaries give rise to Ishibashi states. And the character for the boundary Virasoro algebra just looks like this. It's Q in this case is e to the minus 2 pi t. And this just gives you the contribution of the primary itself, but it's decorated by this eta function, which gives the contribution of all the descendants in the Ishibashi state. And the difference between the vacuum character and the non-vacuum character for h equal to 0 is just this additional factor 1 minus q, which cancels the L minus 1 descendants. Okay, so that's the expansion in the closed string channel. In the open string channel, we cut along an interval like that. And it's convenient to just rescale this whole picture by 1 over t, so that the length of the cylinder is pi, and the length of this thermal circle is 2 pi over t. In this picture, we can think of the partition function as a trace over the open string Hilbert space of this evolution operator, where now we are evolving by time 2 pi over t. And correspondingly, we can expand it in characters of the bound reversal algebra. The first one is the vacuum. The vacuum is always present because we are choosing the two conditions to be the same, alpha and alpha on both sides. And then there is a sum over the non-vacuum characters. So what we found is this condition, which is the Cardic condition, where the left-hand side is the sum over the closed string channel, the right-hand side is sum over the open string channel, and the boundary entropy appears natural as a parameter, multiplying the closed string vacuum. And on the other hand, the open string vacuum is unit normalized. That's because there is only one identity in the open string Hilbert space. Okay, and in the rest of the talk, we won't use anything but this equation to prove some bounds on boundary entropy. Okay, any questions so far?
Yeah, maybe I have a naive question. How do you, so from the open string channel to the closed string channel, or the other way around, you rescaled the coordinate by 1 over t, is that correct?
It's not really a difference between the open and closed string, but I mean, I was just saying that these two pictures are the same picture in a CFT, where the lengths on the right are 1 over t times the lengths on the left. I mean, this statement doesn't depend on whether we are in which where we are cutting. There's nothing. Okay. It's just a general statement about a CFT. It's just convenient to use this normalization in the open string channel, because conformal dimension in the open string channel are the same as energies on an interval of length pi up to some Casimir shift. So that's why it's more convenient like this. Energy is just a scaling dimension minus, well, I should probably write it as h minus u over 24, where this equation is true if the length of the interval is pi. Otherwise, it's going to be rescaled by something like 1 over t. Okay.
Thanks.
Any more questions?
Can I ask a question? I think this is probably pretty stupid. I'm just confused by something. So you're not really.
I'm sure it's not stupid, Mark.
Yeah. So you're saying the coefficient of the identity in the vacuum is 1. That's like saying that you interpret G as the G of a single of an elementary brane, right? Because this equation I can multiply by a constant. The only thing you're measuring is the ratio of the two. But then are there any G functions for non-elementary branes? So I sum up things and I get maybe can I get cross terms or some G functions that are only there for non-elementary branes that you're not automatically throwing away? Or all the G functions are just the sums? I don't know if I was clear.
I'm not sure if I totally
yeah. So I mean, let's take a non-elementary brane.
I think it's a statement is generally true that there is a set of elementary branes for which this equation is true with coefficient 1, and such that all other branes can be obtained as positive integer combinations of these elementary branes.
Okay, so it's just like that. There's no, because if I sum, I could worry about, like in the partition function, if I sum elementary branes about cross terms in the overlap, but probably, yeah, but actually, yeah. So the point is that the G function is just the identity in the bulk channel, so there's no cross term. It's just the identity coefficient. Okay, thanks.
Okay. Okay, so, since you seem to have answered your own question, I don't have to think about it. But it's not something I have thought very deeply about. Okay, just a couple of comments about what I said so far. So another way to see that the G function measures the number of degrees of freedom is to consider this similar partition function that we just discussed in the high temperature limit. So if you interpret it as a sort of a thermal partition function of the open string, high temperature corresponds to taking T very large, so taking the cylinder very long, or in other words, the thermal circle to be very short. That's like high temperature from the point of view of the open string. And in that case, the partition function is dominated by the vacuum character in the closed string channel, which looks like this. And this just tells you that the G controls the asymptotic density of states, because the thermal partition function, the high temperature limit, is determined by the asymptotic density of states, the high energy in the open string channel, and there is this exponentially increasing piece which is universal. Well, it only depends on the simple charge of the bulk theory. It's independent of the boundary condition, but the dependence on the boundary condition is controlled by this finite piece, which is precisely the boundary entropy. So that's why G measures the number of degrees of freedom in the open string Hilbert space. Was comment number one. Comment number two is that there is a very special circumstances in which you can classify the allowed boundary conditions. And this is the set of circumstances is when the bulk CFT is a diagonal RCFT. Perhaps the diagonal is not necessary, but let's focus on diagonal RCFT. And let's suppose that the boundary conditions preserve the full chiral algebra of this RCFT. So there's some finitely many primaries with respect to some chiral algebra in the bulk, and alpha preserves this chiral algebra. Then you can show that the set of solutions, so the boundary conditions, is in one-to-one correspondence with the bulk with the primaries of the chiral algebra W, and these bulk one-point functions labeled by the boundary condition I and the bulk operator J is just given by this ratio, where S is the modulo S matrix. So it's a matrix which tells you how torus characters transform under the S transformation. And in this case, the Verlander formula, which is satisfied by the modulo S matrix, implies the Carde condition. So then there is essentially nothing more to be done. But I want to emphasize this is a very, very special set of circumstances. And in general, even if you fix the bulk theory to be rational, in general, we have nothing near a complete classification of the possible boundary conditions. It is only if you, on top of that, on top of rationality, assume that alpha preserves the chiral algebra. Now, of course, we always want to assume that alpha preserves the Virasoro, but not necessarily the full chiral algebra. So today, we are going to assume neither rationality of the bulk theory or indeed any symmetry beyond Virasoro. And we are going to use the Carde condition to derive bounds in this space. So in the space of these four parameters, the four parameters are the central charge of the bulk theory, the entropy of the boundary theory, and two spectral assumptions. So we'll assume that the lightest scalar in the closed string channel has dimension at least some value called delta gap. And similarly, in the open string channel, we'll assume that all the non-identity primaries have a dimension above some age gap. Okay, so these are the gaps in the closed and open string channels. In particular, there is a natural assumption that we can make on age gap namely that the boundary condition is stable. Stability is just a statement that the H cap is greater than or equal to 1. This is just a statement that there are no relevant operators on the boundary. Relevant, of course, just means less than 1. I mean, no relevant operators besides identity, of course. And in the context of string theory, this is the same as saying that there are no open string tachyons. And that's because the mass of open string state ending on some D-brane is given by this formula where we have h minus 1. And so relevant boundary operators correspond to tachyonic states. So if we have this assumption, this means that our D-brane is at least perturbatively stable. All right, so as I already said, probably at least 10 times, we'll derive upper and lower bounds on G at fixed C under these spectral assumptions. And the technique that we're going to use is the bread and butter technique of the conformal bootstrap, namely the numerical and analytical functional bootstrap. This is a technique that was introduced into the conformal bootstrap by this seminal paper by Retazzi, Coftoni, and Vicky. And in the context of modular bootstrap for the torus partition function, it was first used by Simeon Hellerman. All right, so this is just the repetition of the Carde condition. It is a constraint on the CFT data, which holds as a function of a parameter t, where t, well, a priori it was a positive real number, which measured the length of the cylinder. But in fact, this condition can be analytically continued to any t whose real part is greater than 0. This won't play such an important role, but we can just restrict to the positive real axis if you wish. And the idea of the functional bootstrap is to expand this condition around t equals 1, which is sort of the point, is the crossing symmetric point. There's a fixed point under t goes to 1 over t. And consider linear functionals, which are linear combinations of derivatives with respect to tau evaluated at this crossing symmetric point. So a general finite linear combination looks like this. There is some truncation order, capital N. And typically we fix N, so it's like working to some finite truncation, finite precision in analyzing this equation. But the point is that no matter what N is, we'll always derive rigorous bounds on the quantities involved. In particular, here are constraints on the functional to derive upper and lower bounds on the G function. So if we want an upper bound on a G, we want to find linear functionals which act as follows. They act like 1 on the closed string vacuum. They act positively on all the bulk operators, the closed string operators above delta gap, and they act negatively on all the boundary operators above H gap. Okay, so for simplicity, I'm going to denote this, this H tilde. T is just the same thing as H1 over T. So the twiddle stands for switching T and 1 over T. Then if we have such a functional, by acting the functional on the Carde condition, it follows that there is an upper bound on the boundary entropy that looks as follows. It's just given, the upper bound is just given by the action of the functional on the boundary vacuum. And to get the best possible upper bound, we want to minimize this right-hand side. Similarly, to get a lower bound on the boundary entropy, we still want to act like identity on the closed string vacuum, but now we switch the positivity and negativity of the action on closed string and open string channel. And then there is a lower bound given again by the action on the boundary vacuum. And to get the best possible lower bound, we want to maximize the action on the boundary vacuum. This search for the best possible functional at a given truncation can be implemented quite conveniently using SDPB, semi-definite programming package written by David Simmons-Duffin and Walter Laundrie. So let's now discuss the consequences. first, as a simple warm-up, let's consider theories with C equal 1. So the only thing we'll assume is that central charge is 1. We'll assume that the boundary condition is stable. So H gap is greater or equal to 1. And we are going to vary the delta gap in the range where it can lie, which is between 0 and 1/2. So why does it stop at 1/2? Well, it follows from the torus modulo bootstrap that for C equals 1 theories, the upper bound on delta gap is 1/2. This is saturated. So delta gap 1/2 is saturated by the SU2 WZW model at level 1. And so here's a picture of the bounds coming from the functional bootstrap. The red dots are the upper bound, and they seem to be very close to 1/4√2, which is precisely, which, as we will see, is the value of the boundary entropy in the SU2 WZW model. The black dots are the lower bound, and there are some additional features. So let's discuss the additional features. The blue curve, the blue and magenta curve, and also the green dots show some specific boundary conditions. The blue curve is the Dirichlet boundary condition of in the free boson on a circle, so the unorbifolded circle. In which case you can compute that the boundary entropy is just the delta gap to the 1/4. The delta gap comes from some vertex operator, and you can compute this to be the G for the Dirichlet. And you can see that asymptotically as we approach the self-dual point. So the SU2 WZW model is of course a self-dual point of the circle, of the free boson on a circle. And asymptotically as we approach this point, the lower bound seems to be saturated by these Dirichlet boundary conditions. So that's encouraging. Then the magenta curve is also the Dirichlet boundary condition, but in a different branch of the C plus moduli space, namely the orbifold, where we modeled by the Z2 symmetry to get a free boson on an interval. There, the boundary entropy is given by the 4th root of delta gap over square root of 2. So that's this curve. And this one also needs to be saturated, but only at the endpoint. The endpoint corresponds to delta gap equals 1/8. And the reason there isn't this endpoint is that delta gap in the orbifold can never be greater than 1/8. And that's because the twist fields have dimension 1/8. But it's precisely at this point that the bound needs to be saturated. Finally, the green points correspond to boundary conditions in the 3 sporadic points, the isolated points in the C cosine moduli space, coming from modding out the SU2 WZW model by A4, S4, or A5 subgroup. And in this case, the lower bound seems to be again quite closely saturated by some specific boundary conditions in these orbifolds. Now, I should say that they are not exactly saturated, but they can be made to saturate by making extra assumptions about the bulk spectrum. So this is another general theme that we explored in the paper, that besides just assuming some delta gap, we can fix the bulk theory, which means fix the spectrum of scalar primaries in the bulk, and only impose positivity of the functional on that discrete set of bulk operators. This will improve the bounds, and in fact, they can be made to saturate by these extra spectral assumptions, even in these 3 points. So the lower bound is going to go up. Okay, the feature that I want to emphasize is that if we set delta gap equal to 1/2, so that's over here, the upper and lower bounds are very close to each other. They are just 1/2 to the 1/4 to a very good precision, which is the correct value for the identity brane in the SU2 level 1 WZW model. So it's natural to conjecture that if we assume that we have a stable brane, sorry, this is not a conjecture. This just follows from the classification of branes in this model, that in fact assuming stability and the fact that we have a SU2 WZW model, it follows that the partition function on the cylinder is uniquely fixed to be that of the identity cardiobrane. So this is the identity character in the boundary channel. And this statement actually seems to be true for many other in many other cases. So for example, for c equals 2, the plot looks as follows. So let's assume that the boundary condition is stable, and let's vary delta gap, this time between 0 and 2/3. 2/3 again is the general upper bound on the delta gap at c equals 2. The upper bound is saturated by the SU3 level 1 WCW model. The red curve is again the upper bound, which seems to be quite independent of the value of the delta gap. And the black curve is the lower bound, which now depends on it, but they very nearly meet at the maximal value of delta gap, where they are both very close to 1/3 to the 1/4, which again is the value of the boundary entropy for the identity cardiobrane in this WCW model. Here's a picture of the spectra. So one nice thing that one can do using this functional Bootstrap is that for the saturating theory, you can extract the spectrum which solves the Cardiac condition. And here are the spectra corresponding to the saturating case for the upper or lower bound. I'm not sure which of the two, but since they are so close to each other, it probably doesn't really matter. The bulk spectrum is precisely the bulk spectrum of the SU3 level 1 WCW model. We have two towers of primary spaced by 2. That's because there are two bound characters, and the boundary spectrum just consists of a single character, so of a single tower of states with integer values of h, which just comes from expanding, this the identity character in the boundary channel. So there's only one tower of states with respect to this maximal SU3 Carl algebra.
Can I ask
more general? Yeah.
So in this SU3 case, can you also prove that that's the only brane, or because here you're not assuming rationality, right?
Yeah, we are. We cannot. Yeah, I think we cannot prove that.
So then this is a true numerical result that you cannot prove otherwise.
That's right. I think basically the branes, the general conformal branes in the CFT have not been classified, unlike for the SU2 level 1 WCW model. So this is a new prediction for what basically it says that the only stable brane, well, all the stable branes in this CFT have the same character, same similar partition function, and it's either the identity brane or any other brane which is obtained by acting with some symmetry on it.
Thanks. Thank you.
Very good question. And more generally, this statement seems to generalize to a family of CFTs, which is sometimes called the Deligne-Svitanovich family. This is a family labeled by. Is there a question? This is a family of WCW models at level 1 labeled by simply laced, so not simple, but labeled by groups, Lie groups of the following type: SU2, SU3, G2F4, spin 8, and E6, E7, and E8. And we studied the Cardiac condition numerically in each of these cases by varying the central charge, and by imposing this and perhaps some spectral assumptions coming from the bulk theory. And we convince ourselves that numerics seems to imply that the cylinder partition function on these assumptions is uniquely fixed to be that of the identity brane, where identity refers to the character of the full Cairo algebra of the theory. Now, I want to discuss in more detail the C+8 case, because in this case, we can actually prove this statement analytically. For C equals 8, this is the corresponding plot. There is an upper bound on G, which is 1, independent of the value of delta gap, and a low. in this point, we are not assuming that we have the E8 WSTW model. We are just assuming central charge equal 1, stability, and some value of delta gap. And the lower bound is increasing function, which meets the upper bound precisely at delta gap equal to 2. For delta gap equal to 2, there is again a unique bulk theory, which is just the E8 WSTW model. And this is the upper or lower and upper bound that we find on G at using 127 derivatives. You can see that they are very close to each other. They're basically equal to 1 to 6 decimal places. And well, so it's natural to conjecture that these bounds will eventually saturate, will be equal to 1 at infinite truncation, and that the unique consistent cylinder partition function, which corresponds to a stable brane, is that of the identity brane in the E8 level 1 WSTW model, where the partition function looks as follows. It's the ratio of Eisenstein series and the H power of the Dedekind eta. And it's natural to ask whether we can actually prove this analytically. The answer is yes. So one of our main results is the following theorem. So the theorem can be stated as not referring to necessarily E8 WSTW model. It's a general statement. So it says that if we have some alpha, some boundary condition, conformal boundary condition in a unitary compact CFT with central charge equal to 8, then if the boundary condition is stable, then there is a rigorous upper bound on the G function equal to 1. On the other hand, if the bulk gap is greater than 2, then there is a lower bound on the G function, which is 1. And either of these inequalities is saturated by a unique cylinder partition function, which is just that of the identity brane in the E8 level 1 WSTW model. It's also the third root of this modular invariant. A simple corollary of this theorem is that if you now focus on the E8 WSTW model, we can say that every conformal boundary condition in this theory satisfies the lower bound, G is greater than 1, and also an upper bound on the boundary gap, which is equal to 1. And furthermore, the following statements are equivalent. The lower bound on G is saturated if and only if the upper bound on the H gap is saturated, and that's also if and only if the cylinder partition function is precisely this one. Right. So this first lower bound follows from this statement where we are fixing the bulk theory to have a delta gap equal to 2, so this lower bound is true, and the upper bound on H gap follows. Well, if we assume that the H gap is greater than 1, then we can use this bound, right? So, well, and anyway, maybe it's better if you just stare at this result than if I try to explain it. But I think that this is sort of the general statement about all C equals 8 theories, and this is a corollary for the E8 WSTW model. There is a completely analogous.
Can I ask
you?
Sure. So I remember both a paper by Connecting and Company, and in your paper you point out that there's some specific gap of order C-1 divided by 24 that you need to impose in order to get non-trivial functionals. How does it work here? Because here, yeah, is it automatically satisfied? Because 8 minus 7 divided by 24 is still less than 1, so this condition you're imposing is stronger. Okay, so this is how it works. So you could not run this argument for arbitrary large C. Okay,
that's right. That's right. Yeah. This is just about C equals 8. This
okay.
particular page.
Thanks.
There is a completely analogous theorem for C equals 24, which, in the interest of time, I'm not going to spell out, but basically all the gaps get rescaled by 2, and the corresponding saturating theory is the monster squared. But feel free to ask me about this later if you want. Okay, so these are some interesting theorems about boundary conditions at C equals 8 and C equals 24. And how do we actually prove them? So the idea of the proof is to analytically construct the functionals which certify the exact saturation. So if we construct a functional which gives us the optimal bound, that's a proof of the bound, right? In particular, we want to construct a functional that has the following structure of zeros. So to prove the upper bound on the boundary entropy for c equals 8, we want a functional that has zeros at the spectrum of the E8-WST model, so 2, 4, 6, and all the positive even numbers. And it should be non-negative for all bulk delta. And there's a similar structure in the boundary channel. Okay, and it actually turns out that given these constraints on the structure of zeros, of how it acts on the bulk and boundary characters, there's a unique functional that does this. Unfortunately, there are very few situations where analytic functionals have been constructed. Well, originally they were constructed in my paper in the context of the 4-point function on a line. And it's possible to uplift this construction from the line to the cylinder partition function by thinking of the cylinder partition function as a 4-point function of these end of the, well, these sort of defects, where there's a conformal transformation mapping this picture with 2 intervals cut out into the annulus. So basically the cylinder partition function is a 4-point function of certain primary operators, which live at the endpoints of these cuts. This is very similar to what was used in my paper with Tom and Leonardo in the context of modular bootstrap, where we use this to improve the Hellerman bound from c equals 6 to c over 8 at large C. And finally, this technique of analytic functionals in the context of the modular bootstrap is equivalent to the solution of the sphere packing problem in 8 dimensions and 24 dimensions, where it was actually these functionals were constructed by Vyazovska for the E8 lattice and by Vyazovska and her collaborators for the Leech lattice. But yeah, the details are a little bit technical, and I'm already out of time, so yeah. Well, the basic idea is that these functionals are constructed as some contour integrals in the T plane. Okay, and now just small final results. You can ask if there's a universal upper bound on this G without assuming a specific bulk theory, and there is. So this is the general upper bound only assuming stability. Upper bound on G. You can see it's some curve which only exists when C is less than 25, and the reason is that, as Marco already mentioned, we need H gap to be greater than C minus 1 over 24, because otherwise we can always add the bulk vacuum character to the cylinder partition function and increase the boundary entropy as much as we want, and it will not violate positivity in the boundary channel. So this is the general upper bound. Finally, let me just mention consequences on these end of the world branes. So that's in the context of ADS3 CFT2 when we consider a weakly coupled theory in the bulk in ADS3. Weakly coupled theory means that the central charge is much greater than 1, because the central charge just measures the size of ADS in the Planck units. Now, Takayanagi, in a paper in 2011, considered he constructed boundary conditions for the CFT2, which come from end of the world branes in ADS3. So the boundary conditions, well, these end of the world branes, they are specified by their value of the tension. T is the tension, and the picture looks as follows, roughly speaking. So here X and Y are spatial directions, where X is the boundary of ADS, and Y goes into the bulk of ADS. So the upper half plane here is ADS, and time runs perpendicular to the picture. So the boundary CFT is this blue line and the boundary condition is the red dot, because you should imagine that there is a third direction, the time direction perpendicular to the screen. Now you can compute the boundary entropy for this setup for the boundary brane, and you find some number which scales linearly with the central charge. So the logarithm of the entropy is linear with the large central charge, and the coefficient is controlled by the tension of this brane. So yeah, I should say that the end of the world brane is this skewed line, where the angle of this of the brane with respect to the boundary is controlled by the tension. So there is some relationship between the angle and the tension. Okay, and now the natural question that you can ask is if there are some bounds on this tension, or in other words, on the boundary entropy, in the context of pure gravity. I mean, of course, we don't really know what pure gravity should mean as a full quantum theory, but let's just assume that we have a boundary CFT, which is dual to pure gravity. So its gap should be of the order of C/12. That corresponds to the BDZ black holes, right? And you can also show that in this end of the world brane setup, the boundary gap, or the gap in the boundary channel, should be of the order of C/24. Now, you could of course argue with this, because you could say, well, what about some subleading corrections? And these subleading corrections will be important at large C in our setup. But let's just do the simplest possible thing, and let's literally set delta gap to be C/12, H gap to be C/24, and let's run our numerical machinery to prove upper and lower bounds on the boundary entropy. And what you get is that at large central charge, there are non-trivial bounds. In fact, that the logarithm of the boundary entropy is bounded by this C/6 times some universal number, 3.29, blah, 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 which gives you a bound on the absolute value of the tension being 0.997. So a priori, this is bounded by 1, and the Cardy condition cuts it down to something just a little bit less than 1. Yeah, so you could say we made some very strong assumptions by making these assumptions about the bulk and boundary gap. And in fact, if we decrease this just to C-1/12 or C-1/24, the bound is gone. So it's not a very universal prediction, but at least it shows you that even in this context, the boundary modulo Bootstrap has a chance to be constraining. Okay, so that's the end of the results, and let me just tell you something about possible future directions. One future direction is to consider supersymmetry. So consider stable boundary conditions in the presence of supersymmetry, which are of course relevant for study of D-branes in superstring theory. Another natural direction would be to combine the Cardy condition with the Banach two-point function constraint. So this is just another of the 4 constraints that I listed earlier, where we equate the Banach two boundary OPE of 2 bulk operators with the OPE of the 2 operators in the bulk. And finally, it would be fantastic to extend these analytic proofs of optimality that we had for C = 8 and 24 to extend them to other values of C. For example, for C = 2, we had this nice picture of the spectrum for the SU3 level 1 WZW model over here. And in this case, the corresponding analytic functional has not been constructed, but it seems to be a nice test case for extending this technique of analytic functionals beyond the well-studied cases of C = 8 and 24. And this should be an inspiration for more general analytic functionals, like for interacting CFT, say the 3D Ising model or something like that. So thank you very much for your attention, and sorry for running over time.
Thanks for the very nice and clear talk. I think we still have time for some questions.
Hello, yes, I have a question. So thanks a lot for the nice talk. I'm wondering about the stability condition that you have. So it's a stability condition on the boundary fields and the bulk fields. And could you relax it to say only have a stability condition on either of the two?
Yeah, in fact, good. It's a great question. So this is something that I didn't emphasize, but but which is true, that in general, to get an upper bound on the boundary entropy, it is enough to impose a gap in the boundary sector, and vice versa. To get a lower bound on the boundary entropy, it is sufficient to impose a gap in the bulk sector. So this is exemplified by this theorem at c equals 8. You see that just assuming c equals 8 and a stability in the boundary sector gives you an upper bound on G function without assuming anything about the bulk spectrum. And vice versa, just assuming that the bulk gap is at least 2 gives you a lower bound on the G function. And this is like a general statement. You know, so somehow you would, yeah. The physical interpretation of this first condition in a concept string theory would be that if you want your D-brane to be stable, it shouldn't have a tension which is too large. If you start increasing the tension of the D-brane at will, then eventually it will become unstable. So that and this statement is sort of independent of the bulk spectrum. But yeah, hopefully this.
Okay, yeah, that helped a bit. And so I guess relaxing both of them would be asking too much. So
relaxing both, yeah, without assuming anything, I don't think you can get.
Yeah,
you can see in these pictures, right? Well, already if we relax delta gap to be very small, then the lower bound on G goes to 0, so it becomes trivial. But of course, in this picture, we are not relaxing the stability in the boundary channel, so it's not really that relevant. Well, in any case, the bounds only exist if the precise statement that is that the upper bound only exists if H gap is greater than C minus 1 over 24. So you need a non-trivial statement, and the lower bound on G only exists if the bulk gap is C minus 1 over 12.
I think you stopped. No, it's. Yeah, it wasn't what you were writing was not appearing.
Okay. So yeah, these are the necessary conditions for a bound to exist.
Okay, thanks.
Can I just ask if these conditions are relaxed? I mean, I understand that you cannot find bounds with the method you use, but are there counterexamples, or is it a shortcoming of the method?
Yeah, no, the reason that in this case the bound don't exist is that you can basically add the copy of the either bulk or boundary vacuum character, which, however, in the other channel will correspond to a continuous spectrum. If you just take the vacuum character and expand in the cross channel, you will get a continuum, and that of course violates some kind of compactness assumption. So you could hope that by imposing discreteness of the spectrum and some other constraints, you could go beyond this sort of roadblock. By the way, one thing that I didn't impose is integrality in the boundary channel. If we expand, you see that in a boundary channel, we just have characters with coefficient 1. So in general, this is just degeneracy of a given H. And I wasn't assuming that these coefficients are integers at all. So maybe using this, you could go beyond the roadblocks of C minus 1 over 24.
And sorry, the way to interpret adding the vacuum in the boundary channel is then by dividing out, so transferring this to, I mean, in the end, you still want the equation with the vacuum channel with coefficient 1, right?
Yeah,
so
yeah,
you're saying there's some other set of, all the OP data are affected also from in the boundary and in the bulk.
That's right. Yeah, you would add some vacuum character times some positive number and divide by 1 over 1 plus lambda or something. And okay, this would, yeah. This
But
will
it
just
would, yeah, it
rescale.
would violate the integrality, for instance, in the boundary
Yeah, it
channel.
would violate the integrality, but we are blind to the integrality in this functional method.
Right, but that's more than just violating continuous spectrum. Like compactness is something, but okay, violating integrality with still a compact spectrum is worse.
Yeah, you're right. Perhaps just emphasizing the integrality is more important than compactness.
Thanks.
I also have two questions. The first question is that, do you need to assume that there is no null state in the Hilbert space?
Oh, good. Yeah, thanks. I forgot to say that in all of this, I assume unitarity. So we have a unitary CFT.
Okay. And the second question is about this bound from holographic side. That we know there is a Coleman-de bound from for the brain tension. I mean, an upper bound for the brain tension, and if I remember correctly, it's actually given by 16 pi g over the ADS radius. I don't know if like the bound you have here will coincide with that one.
Isn't that just the bound? Is it just the bound which should be saturated when this angle becomes 0?
Right.
Right. So that corresponds to this bound. That's where the tension in the units of ADS radius is 1 in the units that I'm using. So our bound is an improvement over this. Even if you express it for TR, it's kind of small. When you express it for the log G, it looks a bit better. Instead of infinity, you have 3.29. But yeah, it is an improvement over this Coleman-de bound. But I should say it's an improvement under some pretty strong spectral assumptions. So I wouldn't necessarily take this number very seriously, because this number is very, very sensitive to any order 1 corrections to these spectral assumptions.
I see.
Can I make one comment here? Sorry, I just would like to emphasize that this bound, if it was true, it would be extremely important for the story of black hole evaporation in double holography that people are discussing a lot. I mean, you didn't mention, but probably for time. But I mean, if it was like that, because this ratio is essentially how it's the page time, and if you cannot go really arbitrarily close to 1, your page time is like Planck size, so you don't really have a semi-classical picture at all. So it would be very important to pin it down.
Right. Yeah, I mean, it was more like a proof of concept, and in general, what exactly is the boundary in the box spectrum will depend on the details of the Balkan boundary theory. Especially in these order 1 corrections, they can be anything. And as I said, if it becomes C-1/12 or C-1/24, then the bound on the tension completely disappears. So don't take it too seriously.
Okay. Thanks. Yeah, I guess probably that's all for today. Thanks again for the very nice and clear presentation. I really like it. I will stop the recording now.